we're going to look at solving some exponential equations that require logarithms. This comes from the Year 1 book. It's number 85. So if you want to have a look at that, it's at the site just here. I'm not actually going to do the questions in the book. I'm going to do some examples that will allow you to solve these particular questions. Let's start off with some basics. We saw earlier in the course that if we, for example, had 2 to the power of x is equal to 8 to the power of x minus 1, we could look at solving this exponential equation. It's called an exponential equation because the unknown is in the power. All we would do with this particular example is write both of these bases as powers of 2. So we could write this as 2 to the x is equal to 2 to the power of 3 raised to the power of x minus 1. Now we have the base, which is 2, the same. We can simply equate the powers. So we can say from here that x is going to be equal to, and using the rules of indices, we're going to have 3 lots of x minus 1. So all we're going to do is go ahead and solve this. So we'll have x is equal to 3x minus 3. Adding 3 to both sides, subtracting x from both sides, we can see that 3 is equal to 2x, and x is going to give us 3 over 2. This was nice and straightforward because we had a base that we could change such that they were the same. What we're going to do in our first type of exponential equations is look when the bases aren't the same or we can't easily make them the same. And we're going to use logarithms for that. So here is an example, and this comes from the first column where we've got the D and E ones. We might, for example, be asked to solve 5 to the power of x is equal to 30. Of course, if this was 5 to the power of x is equal to 25, that'd be nice and straightforward. 5 to x is 125, that'd be nice and straightforward. But because we have now this value of 30 not being a power of 5, we're going to use logarithms. The easiest way to do this is take base 5 logarithm of both sides. So if we take logs of both sides, what we can simply do is say now that log to the base 5 of 5 to the power of x is equal to log to the base 5 of 30. Hopefully you know that this is just going to give us x. If we have now log to the base 5 of 5 to the power of x, that can simply go as x is equal to log to the base 5 of 30. All this is asking me now is what power is 5 raised by to get 30, and we'll do that in a calculator. So hopefully you've got one like this. If you're looking at this a few years down the line since I made it, you might have something different, but this is the one that we're using currently. There's my log button just here. I'm going to take base 5 and I'm just going to type this in, and it's log to base 5 of 30. That gives me 2.11. So to 3 significant figures, we'll go 2.11. You can, of course, check. With this particular equation, it's not really necessary to check because you can see that you haven't got many steps in it. But if I just go back and I type in 5 to the power of the answer, this is going to have to give me 30. As we can see, that works, so we're right. With these particular ones, we might have something slightly more challenging. You might, for example, have 4 to the power of x plus 7 is equal to, let's say, 18. You might even have something here, and it might be, let's say, 3 times 4 to the x plus 7 is equal to 18. This shouldn't cause us any problems. All we would have to do is simply divide both sides of the equation by this value. So in this case, it works out quite nice. So we'd have 4 to the x plus 7 is equal to 6. At this stage, we can write the exponential equivalent by taking logarithms of both sides. You can, of course, take base 4 on this one because we got here 4 to the x plus 7. So we can simply say that x plus 7 is equal to log to the base 4 of 6. This, of course, is just a value, it's just a number. So we can now say that x is equal to log to the base 4 of 6 minus 7. This answer here is what we would call exact form. So it's not a decimal answer, it's given in terms of a log. So if you're asked to give an exact answer, especially when you're working with a natural log, this is what we have. We can write that as a decimal. So if you want to get it as a decimal answer in the calculator, we've got log to the base 4 of 6 minus 7. That's going to be negative 5.7. And again, you can just check that that works when you're going back in with your solution. So let's write this out. We've got x is equal to negative 5.71. So that's three significant figures. So let's just check that that answer works. If we do 3 times 4 to the power of my answer, just here, plus 7, we should get this value of 18. And we get exactly 18. So you can see that works. On a side note, with these particular examples, I was taking the base of this, the logarithm. The base of a logarithm was this value here. We didn't need to do that. So for example, we could pick it up here. You don't have to take base 4. In these particular examples, it is easier to take base 4 because it makes your calculations less. Let's say I didn't do that and I simply wrote that 4 to the x plus 7 is equal to 6. If we took a different base, for example, base 10, and hopefully you've met that base 10 is just log, we could take logs of both sides. And we could write that log of 4 to the x plus 7 is equal to log of 6. So taking base 10 at both sides, I can now bring this power down using the power law. So I'm going to have x plus 7 multiplied by log 4 is equal to log 6. I want to solve for x, so all I'm going to do is expand the brackets here, and I'll have x multiplied by log 4. Remember, log 4 is just a number, plus 7 times by log 4, and that's equal to log 6. So what we've got here now is x on this side. We only want x on that side, so we're going to write that x multiplied by the log of 4 is equal to the log of 6 minus 7 log 4. As you can see, this is far more laborious. There is a reason I'm showing you this, though, but I certainly wouldn't use it for this particular type of equation. And we can write now that x is equal to log 6 minus 7 log 4 all over log 4. If you type that in a calculator, you will see that it will give you exactly the same value as we've got just here. So you can put it through your calculator if you want to go for that. I've used base 10. So base 10, we hit shift, this lovely gold button, and the value here, and this will give us base 10 log. So what we'll have is log of 6 minus 7, and then we've got log of 4 over log of 4. So log of 4, and this should give us that negative 5.7, etc., etc. You're probably going to say, why did I do that? The reason I've done this is the next type we're going to look at is where we have unknowns on both sides. So far we've only had the unknown on one side. We might, though, have an exponential equation where we have unknowns on both sides. So if we look at this example and we had 5 to the power of 2x plus 1 is equal to, for example, 7 to the power of x plus 3. I'm just choosing these. There's no particular reason that we should have these numbers. I'm just choosing them. As you can see, taking base 5 or base 7 would make things slightly easier on one side. The issue is, though, we can't take base 5 of this side and we can't take base 7 of that side. What we must do is keep consistent. So you can take base 5 of both sides, you can take base 7 of both sides, but whatever you do to one side of the equation, you must do to the other to preserve the equality. Now, I'm going to take base 10. The reason I'm going to take base 10 is that it will keep your work nice and clean, and also it's easier to write. So what I'm going to do, in order to bring these powers down and solve this equation, I'm going to write log of 5 to the power of 2x plus 1 is equal to log of 7 to the power of x plus 3. I can now bring these powers down. So using the power law, we've got 2x plus 1 multiplied by log 5 is the same as x plus 3 multiplied by log of 7. Log 5 simply means what power is 10 raised by to get 5. Log 7 simply means what power is 10 raised by to get 7. They're nothing magical, they're just numbers. What we've got to do here is solve for x. So I'm going to expand these brackets on both sides of the equation, get x on one side, and then get a value that we'll have first in exact form, and then we will go ahead and write that as a decimal. So we're going to have 2x log 5 plus 1 log 5 on the left-hand side of the equation. That's going to give me x log 7 plus 3 log 7 on this side. So let's get the x's on one side, and I'm going to have x on this side. Hopefully you're going to see I'm going to cut the time down. This is going to give me 2 lots of log 5 minus log 7. Over this side we're going to have the 3 lots of log 7 minus 1 lot of log 5. There are, of course, log laws that you can bring these powers up. There's no real advantage of doing this as log of 5 squared because we're going to calculate it. Just look out though that some questions might want it in a particular form and they might get you to go for something. So just be aware that log laws can be employed. I'm just going to write this now as x is equal to 3 lots of the log of 7 minus the log of 5 all over 2 log 5 minus 1 log 7. So straight for the calculator with this, and we're going to have, I'll just do it to a side so I can see what I'm doing. We're going to have 3 lots of the log of 7 minus now the log of 5. And that is going to be over now 2 lots of the log of 5 minus the log of 7. So let's see what that gives us. That gives us 3.32. So x is equal to 3.32 to 3 significant figures, or in exact form, it's this just here. So 3.32. A nice check-in mechanism now is to put this back into this equation. It takes a minute, but it might be worth it, especially if this question is worth 3 or 4 marks in an exam. So if I do 5 to the power of 2 lots of the answer plus 1, and I subtract away from that, if I just come out of there, and I subtract away from that 7 lots of, let's put the power in, the answer plus 3, I should get 0. All I'm doing on this particular equation is subtracting this from both sides. So if we do that one minus that one, we should get 0. Obviously, there are other ways of checking it, but that gives me exactly 0, so we know that this answer is good. If we look at this just here, what I could have done instead is not use base 10. So it doesn't matter which base we use. So for example, if you want to, and you've met the natural log, and if you haven't, you will shortly, we could have done this as 3 lots of ln. Let's actually put that in. 3 lots of ln. So I need to hit shift on that one. So I've got 3 lots of the natural log of 7 minus the natural log of 5. This is a base E logarithm. Again, nothing majorly different. It's just got a different base. And then we can put this in and we will get exactly the same answer. No, we won't. Have I typed something in wrong? What have I typed in wrong? We got 1.78. That's what I've typed in wrong. I've put log instead of, there we go. Be good if I could put it in shift log of 7 rather than the wrong button. And that'll give us a 3.32. So as you can see, it doesn't matter. But as you've just seen from my error, you obviously can't change base halfway through. So there we go. So that's one of those. you might get a slightly more challenging example of this, but it shouldn't be an issue. So some questions might say, for example, let's go for something, for example, like 3 to the power of 1 minus 4x is the same as 5 lots of 2 to the power of, let's go for x plus 3. So what we've got here now is a multiple of this. It shouldn't really matter. We can, again, take logs of both sides and use log laws. So with this one, I'm going to take base 10. So I'm going to write here that we've got log of 3 to the power of 1 minus 4x is equal to log of 5. And I'm just going to write this now as 5 times, we've got this 2 to the power of x plus 3. So in this particular one, I'm going to use a couple of log laws. So I'll write one more line out. What we're going to have before I bring the powers down is log, and that's base 10, of 3 to the 1 minus 4x is the same as log. And at this stage, I can use the addition law for logs. We know that log A plus log B is log AB. So all I'm going to do is split this up. And I'm going to write this now as log of 2 to the power of x plus 3. And then we got the log 5 plus that. Log 5 is the number. Log 5 is basically saying what base is 10 raised by to get 5. So at this point, we're exactly where we were. We've just got some additional value. It doesn't matter. That's going to be on the side without an x because it doesn't have an x in. So using the power law, we've got 1 minus 4x multiplied by log 3 is equal to log 5. And then we're going to have now, bringing the powers down, x plus 3 multiplied now by log 2. So we can go ahead and expand the brackets. And we've got now log 3, so log 3 minus 4x log 3. That's going to be equal to log 5 plus x log 2 plus 3 log 2. So you can do whatever you wish at this stage in terms of getting the x on one side and numbers on the other. I'm going to put the x's on this side purely because I like things to be as positive as possible. So on this side, we're going to have log 3. So we've got log 3 minus log 5. Again, you can combine these if you want and write that as log of 3 over 5. When we're doing this calculation in terms of giving a decimal answer, it's not going to be of any real benefit. But again, if it asks for it in a particular form. So they might say, can you write this in a particular form? And as we got now the subtraction, we could write this as log of 3/5, and then we got minus a log of 8. So you could actually write that as what, log of 3/40 if they want. I'm just thinking of ways they might ask for it, but we're not going to do that because I'm running out of space. So that's going to give us now x log 2 plus 4 log 3. That looks good. So all I need to do is divide this amount by this amount, and we'll see how that goes. So straight through the calculator, let's go for that one. What have we got? So we've got now over here, let's see if I can squeeze that on. We got log 3 minus log 5. Let's hope I can keep the same base this time. Minus 3 log 2 over log 2 plus 4 log 3. Okay, let's see what that gives us. That gives us now negative 0. Let's just write this out. Negative 0.509 to 3 significant figures. Yet again, I'm going to check. Let's just check my calculations were good. So using this here, what I'm going to write is 3 to the power in the calculator of 1 minus 4 lots of my answer minus 5 times 2 to the power of my answer plus 3. If this gives me 0, I know what I'm doing is going to be correct, and that gives me 0. So we know that this value works. It's worth checking because, again, that's it's worth checking. It's just worth checking. Okay, let's look at the other type that we're given in this particular unit, and that's where we can form a quadratic from the exponential equation. So we'll start with a straightforward one, and we will have now 4 to the power of 2x minus 3 lots of 4 to the power of x minus 4 is going to be equal to 0. This should work. So we have here 4 to the 2x and 4 to the x. We're going to use the rules of indices. In the rules of indices, we've seen that a to the power of m raised to the power of n is equal to a to the power of m multiplied by n. We could have written this a different way. What we could have written is a to the power of n multiplied, now, or raised to the power of n, I should say, is a to the power of mn as well. So what we're going to do is use this on this particular equation. So these are the laws that we've learnt in the past. So what I've got here is 4 to the 2x. So I can write this now, 4 to the 2x, as 4 to the x to the power of 2. So we know that these being multiplied can be written in any of these forms, so I'm just going to write it as 4 to the x raised to the power of 2, minus 3 lots of 4 to the x, minus 4 is equal to 0. We can form a quadratic equation or solve a quadratic equation to find the value of x from this. A lot of the time you can use substitution if you find that easier, or you could just factor it. I'll show you how to factor it straight off into double brackets. But generally speaking, what we would do is let p be equal to 4 to the power of x. So if we let p be equal to 4 to the x, this here is going to be p squared. The only reason I don't like this particular method is that students do all of the amazing work, get to the end, solve for p, and then don't actually solve for x. So they end up with p is equal to this and p is equal to that, and get quite excited, which is great, and then don't actually answer a question. So we got p squared minus 3p minus 4 is equal to 0. That looks like it factors. So what would we have here? P minus 4 multiplied by p plus 1 is equal to 0. This gives us now that p is equal to 4, or p is equal to negative 1. We've got that p is 4 to the x. So what we would do from here is write now that 4 to the x is equal to 4, or we've got now 4 to the x is equal to negative 1. We can't have 4 to the x is equal to negative 1, not for a real value of x. So what we just need to do is make sure that we are solving these correctly. So if we look at this now, we've got the graph of y equals 4 to the x. The graph of y equals 4 to the x for real values of x is going to look something like this. So y equals 4 to the power of x. This point here is 0, 1, as we've met before. This exponential curve will never give us a value of negative 1. As we can see, it will never be below that axis. So all we do is write that 4 to the x can't be negative 1. All we've got to do is do this one. Well, that's nice and straightforward. We don't even need logs, because if 4 to the x is equal to 4, well, that's 4 to the x is 4 to the 1, so x is equal to 1. So we've only got one solution from that. You can't take the log of a negative number for a real value. So if we try to do here, for example, you thought, I'm going to go ahead and solve this one. So if we did have 4 to the x is equal to negative 1, the exponential, the logarithmic equivalent of this exponential would be x is equal to log to the base 4 of negative 1. If you put that through a calculator, hopefully you're going to see that this is going to give you a math error, or whatever this one is now doing. Let's put in negative 1, and there we go, there's our math error. We're asking it to do something for real values that it can't do. So that's a nice example of one of those. Let's do a slightly more challenging one of those, and again, this is, we'll form a quadratic from it. You might be told that this is one of those quadratics in disguise. I don't know why they want to be in disguise, but they seem to be something that the books like to do. Let's have a go with something like this. Go for 5 to x plus 15 over 5 to the x is going to be equal to, let's make it 8, make it nice and easy to work with. So again, if you're looking at this, I would be thinking to myself, can I form a quadratic equation or some form that looks like a quadratic equation from this? What I'm going to do here is multiply both sides by 5 to the power of x. If I multiply both sides by 5 to the power of x, I'm going to get 5 to the power of 2x plus 15 is equal to 8 lots of 5 to the power of x. Remember, 5 to the x times 5 to the x is 5 to the x plus x, which is 5 to the 2x. We're back, hopefully, where we were before. We got 5 to the 2x minus 8 lots of 5 to the x plus 15 is equal to 0. So at this stage, we can let p be equal to 5 to the x if you want. I'll let you do that if you want to do that. I'm going to show you another way of factoring it. You could just stick out some double brackets here. So it looks like we've a general quadratic expression that we got. We need two numbers that essentially multiply to give positive 15 and add to give negative 8. So I'm going to go for 5 to the x minus, what's that going to give us? 5 and 3. 5 to the x minus 5 and 5 to the x minus 3. So if you've gone for the p is equal to, at this stage, hopefully you've got these in your double brackets. So solving these, we've got now that 5 to the x minus 5 is 0. So that will give me 5 to the x is equal to 5. And then this one just here, 5 to the x would be equal to 3. Nice and straightforward again. We can just simply do this one without logs, because if 5 to the x is equal to 5 to the 1, then x is equal to 1. This one, slightly more challenging. 5 to the x is equal to 3. So we can write now that x is equal to log to the base 5 of 3. That's just a numeric value. So log to the base 5, there's our log button of 3, and that gives us 0.683. That looks right. That's 0.683 to 3 significant figures. Again, it might ask it for it in exact form. If it asks for it in exact form, x is 1 and x is log to the base 5 of 3. So that was just a bit of rearranging. Let's do one more, because I'm mindful how long we've been going. Let's look at, for example, 3 to the power of, let's see what we can make work. 3 to the power of 2x plus 1 plus, let's go for 14 lots of 3 to the x minus 24 is equal to 0. There's only a slight quirk on this one. Is that we've got 3 to the 2x plus 1 instead of just 3 to the 2x. So all I'm going to do is split this up. What we've got here is 3 to the power of 1 multiplied by 3 to the power of 2x. Remember, with rules of indices, if we've got 2x plus 1, that's 3 to the 2x times 3 to the 1. So that's going to give us this minus 24 is equal to 0. So again, if you want to use a substitution, let p be equal to 3 to the x, we can do. So if we did, or you could just factor it the way I did last time. Let's let p be equal to 3 to the x. What we've got here now is 3 times p squared. Let's put a plus there. That's not equals, is it? Plus 14 lots of p minus 24 is equal to 0. We're going to need to factorize this. Let's see if I can factorize this. I'm going to go, what is this going to be? 3p minus 4. I mean, you can solve this as on your calculator. You can solve for p on a calculator. And what's that going to be? P plus 6. That should work. Let's go for it. 3p squared plus 18p minus 4p. That's good. So what we've got from this now is that 3p minus 4 is equal to 0. So p is going to be equal to 4/3. On this one, we've got p plus 6 is equal to 0. So p is equal to negative 6. Remember, we are not solving for p. We're solving for 3 to the x. So what we can see from this now is that 3 to the x is equal to 4/3. From this, hopefully now you can see that 3 to the x cannot be negative 6. So we can discount this as a valid real solution. So from here, we're just going to write that x is equal to log to the base 3 of 4/3. That goes straight through the calculator, and we'll see what we get. So log to the base 3 of 4/3. That's going to give us 0.26, etc., etc. Again, if you want to check that that works, you can just run it through that top equation. So we're going for 3 to the power of, what have we got? 2 lots of that answer. Where's my answer gone there? Plus 1. Plus 14 lots of 3 to the power of that answer. Close the bracket. Minus 24. This should give us 0. And there we go. So that is the correct answer. So there we go. Half an hour on those the equations that need logs to solve them. So hopefully that's helped. As stated, I've not done the actual answers to the questions, but that should give you now the ability to answer most of these ones just here from 85, and hopefully you'll be able to do some of the more challenging ones.